Good afternoon and welcome to this webinar provided by bobwillisonline.com. My name is Bob Willis and I'll be presenting today's webinar. Before we get started about the topic of today, which is PCB outgassing, I'd first like to introduce you to the control panel, which you have on your screen at this moment in time. Now, the control panel allows you to do a number of things during the presentation. First of all, you can open and close the control panel by clicking on the orange button. This prevents it obscuring your view of the slides during the presentation. You can click on the blue button and this makes the image on your screen or on your projection facility in your conference room go full screen, thus giving you the best view of the slides during the presentation. Now, if you or any colleagues in the conference room with you have a question, all you need to do is type it directly into the control panel. Now, these questions will be answered at the end of the webinar this afternoon. But sometimes it's easier to type a question while you think about it, or perhaps while a colleague has a particular question to ask. So just type your questions at any time during the webinar into the control panel, as indicated here by the red arrow. Just a couple of other things. If you have any technical problems during the webinar, please use the telephone number for GoToWebinar, which was included on your email. You'll also need your reference number and logon. If you would like any other issues to be resolved, that's the best way of doing it and as quickly as possible. I'm unable to assist you during a live presentation. At the end of the presentation, we have a couple of survey questions just on the content, things and topics you'd like to hear about in the future. Just take a couple of moments to complete that. After the survey, we'll be sending you a copy of the slides in PDF format for your future reference. And hopefully that will provide you as a good reference for the future. Now, just a little bit about my background. I've been involved in manufacturing engineering all of my working life. As a mechanical engineer, I've had the pleasure of going to many countries across the globe, providing training courses, both hands-on and theoretical. I also provide a failure analysis service, so if you have a particular process problem or process issue, then all you need to do is contact me, and then we can work out the best way of moving forward. I've also written a few books, defect guides, and regularly attend international conferences. So that's a little bit about me, my activity within the industry in electronic manufacturing. So every month I do a webinar on a different topic, and I've just listed here the next 3 months of webinars and also the topics that will be coming up throughout the year. We have an online webinar demand service if that's what you would like, and also we have an archive system for previous webinars if, again, that's something you've missed out on. So hopefully that provides you and your engineering team the opportunity of providing and understanding some of the technologies we deal with today. So on to our topic of today, which is outgassing of PCBs and how to test them. Now, we can suffer from outgassing from boards on all of the standard processes that we see in manufacture today. So with wave soldering, basically what we see is joints which have voids within them. We normally refer to those as blowholes or pinholes, and that's exactly the same as we get with selective soldering. We can see this phenomena with hand soldering of joints, and we can also see it with intrusive reflow and traditional reflow. And if you're looking at using underfill materials on printed circuit boards, again, that can contribute to voids within the underfill. We can see some voids which are created on reflow soldering where it's related to packages like LGA QFN packages. So again, I'll illustrate how that can occur where it's related to the printed circuit board. So all of what we're talking about really today is the most common faults which are generated by the board. However, I do illustrate other reasons why we can see voids and blowholes and pinholes which are not the PCB as well. but they are part of the through-hole soldering process. So let's start at the start, which is basically outgassing and blowholes. So pinholes and blowholes are the same thing. Some companies refer to pinholes because they're smaller than other holes. So a blowhole is big, a pinhole is small. But really, there is no difference. When a solder joint is in a liquid state, if you've got some volatile material which is actually trying to get out of the barrel of the hole during the soldering operation, the size of the void and the size of the hole is related to when the solder solidifies. So if we take tin lead technology, tin lead, or where we're using 60-40 or 63-37% alloys, traditionally what we would use in non-lead free technology, again we would see this very visibly. When we're talking about lead free, we again tend to see pinholes and blowholes, but sometimes they are slightly different in appearance, as you see from a couple of the examples that I show on this particular slide. And it's fair to say that I've been working both in printed circuit board manufacture and also assembly, so I see it from both sides of the coin where issues come. Now, if we step back for a second and talk about another example of outgassing, we can see outgassing from the solder mask on a printed circuit board. And this is shown up sometimes when we're using underfill materials. Now, for those of you who are not familiar, underfill is a material which is placed underneath large packages like BGAs and smaller flip chip packages to even out the distribution of force applied to the solder joints. It's basically trying to overcome the problem of differential expansion between the component and the PCB. So it's evening out the stress, not taking away the stress, just evening out. So if you've got a material which is liquid or semi-liquid on the board underneath the component and we're trying to cure it, if outgassing does occur from the solder mask, what you're actually going to generate is bubbles. So what you can see in this simple video demonstration is lots of bubbles actually coming out from the solder mask during the heating and curing of the underfill material. So, that's how voids might form in that situation. In a very bad situation, if you were wave soldering a printed circuit board and you've got a lot of outgassing from the solder resist when it goes through the wave, this also could contribute to skipping. This is where we've got surface mount components, chip components, or SOC 23s, which are wave soldered, that actually haven't got any solder on the joint. This is obviously what we call a skip or an unsoldered joint. I prefer not to use terms like insufficient, because insufficient means you haven't got enough, whereas with a skip joint, an unsoldered joint, you've got no solder whatsoever. So those are two examples where outgassing from the solder resist can generate issues in manufacture. Now, in addition, when we've got gassing, what we can see during the soldering operation is voids forming. Now, what I'm going to show you now is a test that can be performed using X-ray. And what you're looking at is examples of through-hole terminations. We're performing what I refer to as intrusive or pin-in-paste reflow. So the solder paste in the hole, there are pins in the holes, and we're reflowing the solder paste as we would do with an intrusive reflow process. And if you look carefully where the barrel of the played through hole is, you can actually see voids. Now, these voids can be generated from the PCB in terms of outgassing, the same as we're going to examine in more detail as we go through the different processes, but these equally can be created by the solder paste and the volatility within the solder paste material. But using X-ray inspection and simulation is a very good way actually seeing what's happening. And the test method I will go through with you to show and allow you to test printed circuit boards is pretty much like this, but a lot simpler and cheaper to perform. But it's just nice to understand there are other techniques as well. Now, if you want to truly understand and also reduce or eliminate pinholes and blowholes, you also have to understand the specification of the printed circuit board and what you're actually buying. The reason being that if you buy a printed circuit board, that board must be specified so you're not actually contributing to the problem. So let's say, for an example, if you buy boards and they are passed or they're made and inspected to level 2 of IPC, that's no bad thing at all. But what you're actually saying is you can have blowholes and pinholes, because within level 2, you can actually have thinner plating than perhaps with level 3, but also, more importantly, you can have voids in the plating. Now, again, it's stipulated within IPC what the criteria is, but the point I'm making is understand the standard. So if you want to guarantee you do not have a board that can contribute to what is perceived as a problem, then you need to think about how you specify it, and need to also understand how you specify the other criteria. Because most people will specify like boards to IPC 600 or the IPC design standard, and in addition, I would like some extra things. And that's what's considered when you're paying or sourcing your printed circuit boards. So please understand what you're buying, because that can obviously affect what you're actually seeing in manufacture. You can't reject things if you're actually buying a product that gives you that particular type of defect, or potentially gives you that type of defect. So just understand the total picture. I do find, with the greatest respect, a lot of customers quote standards but don't understand the standards, which you must do if you're going to quote them. Now, if we're going to talk about blowholes and pinholes, which is our conversation, what's acceptable and what's not? Well, within IPC, there is criteria for blowholes and pinholes. And as you can see from IPC standards, IPC 610 is the standard for plated through holes and solder joints. It will give you criteria for what's acceptable or not. But fundamentally, for a plated through hole after a soldering operation, your criteria is based on the area of wetting. So this is the solder fill of the plated through hole and the area of coverage around the pad and around the pin. So whether there is a void, pinhole, blowhole, is partly irrelevant if you still met the basic criteria within the standard. So all of you will be familiar with the standard, so I'm not going to go into specifics, but just think about that. If you've got a blowhole, a pinhole, but you're still meeting the requirements, then the blowhole or pinhole is really irrelevant. So in terms of wetting and wetting around the pin or wetting around the pad, that's broken down into the three classes, class 1, 2, and 3. And as you can see, you're looking for a wettable area around the complete circumference or a minimum of coverage depending on the criteria. So class 2 is a minimum of 180% around the terminations. So that's the basic criteria. I've briefly mentioned what we're trying to do in terms of buying boards to the standard, which provides you the opportunity of achieving that standard. Okay. So a little bit of background. Where did the original work on blowholes and pinholes come about? Well, a good friend of mine, Dr. Colin Lee, did a lot of work on this in the 1980s. And really, this is the sort of main work that's been done on this particular subject. there really hasn't been a necessity to do anything more because it was quite straightforward and clear after the work that he did. And you can look online and find copies of these reports or download them from the publishers. But basically what he wanted to do was look at the reasons why it occurred, what actually produced the outgassing, and what could be done to try and reduce the problem. So what he did is he took boards from different customers, different users, including some from myself, and he drilled into the solder joints to look and expose the voids within the bulk of the solder. And then what he did was analyze, using mass spectrometry, what was actually coming out from that surface. And he was able to determine, after doing a number of experiments, that basically it was water vapor that was coming out. And that was the material which, when heated, superheated, created the energy to produce voids within the solder joint. So that was how he did that. And at that same time, he was doing other experiments on similar projects using similar printed circuit board assemblies. Now, to capture and look at the degree and also do further analysis, what he did was actually take boards and put them into oil, hot oil, and then capture the volatile material which was actually coming off of the surface of the printed circuit board. As you see in the diagram on the left-hand side, and he repeated the measurements that you saw previously, which are indicated again on the right-hand side. And again, he was able to demonstrate that water vapor was what was coming out of the voids, which consequently would have been left inside during the formation of voids. The same techniques could also be used on bare boards, which was also demonstrated. So not boards that had already been soldered, but boards that were known to give a problem that could actually be tested to analyze what was actually coming out. So basically, what he was able to do is determine what was causing the problem, and as part of the exercise, he was also able to look at the quality, consistency, and thickness of the plating in the plated through hole. Not necessarily referring specifically to standards, but looking at what was actually given to him in terms of boards which may or may not have to be reworked by the particular companies who provided it. Now, so from the basic work that was done, he could determine and show the soldering process, what was actually happening during the process. He had some concerns at that time because of the energy produced during the water vapor turning to steam, that it can actually displace copper from the plated through hole. But as the solder joints were actually formed at that time, there wasn't very much evidence of that actually happening. But there is a lot of energy, as we know, generated as water vapor goes to steam. And again, it's something we've seen with components in the past and also delamination of printed circuit boards. So by doing this, he also was able to give a view with regard to how you could take moisture out of a printed circuit board. And so we could take boards that are known to give a problem, but you could actually bake them for a period of time and see the reduction in the amount of voiding. And we know this from experience, that if you take boards that are known to have a problem and bake them to reduce the amount of moisture, you reduce the amount of outgassing. And that's been demonstrated many, many times. The disadvantage of doing this is that it can affect the wettability or solderability of the board. Now, if your boards are tin lead, solder leveled, or nickel gold, this is fairly unlikely to occur. But if you're using silver, tin, or copper OSP, the more you bake, the more you directly affect the solderability, wettability, and hole fill. this has again been demonstrated many, many times. And there is an IPC standard which gives you recommendations on baking boards, not necessarily just for this case, but for all cases where baking may or may not be required. So, during the exercise, he also looked at the quality of drilling of plated through holes, and it was very obvious from the samples that he examined, and still today, if you've got a board which is being poorly produced, poorly drilled, it is very rough in appearance. So consequently, the copper, electrolyzed copper, and the electroplated copper has got to do more to give coverage to that uneven surface. And of course, at some point, if we haven't got sufficient thickness of copper, then that copper can still be porous and again allow gas to escape during the soldering operation. Hopefully we will be able to demonstrate that to you in the next few slides. So the key thing is quality of plating, quality of copper, minimizing the possibility of moisture being present, and if you can do that, you're reducing the possibility of blowholes and outgassing. So you could obviously look at all the detail within the report, but the key thing is plating, consistency and quality, specifying the right thickness of copper plating in the plated through hole, and also receiving boards which have got a minimum amount of moisture present to start off with, and storing them in an appropriate way. So if we just consider the boards for a second, when you receive boards from suppliers, what you really want is something which minimizes moisture absorption. And plastic bags do not eliminate moisture absorption. And although you have indicator strips which give a suggestion of what the relative humidity has been within the plastic bag, I personally don't think it's a very good guide. What you have got to do if you want to guarantee, to eliminate moisture content, you've got to look at a sealed bag, just like you use for components. If you're going to reduce the possibility of outgassing and blowholing, then again you've got to look at copper plating. So my recommendation today would be a minimum of 25 microns of copper in the plated through hole, and virtually that will eliminate the possibility of voiding and outgassing if you in turn also try to reduce significantly the moisture content in the board prior to the soldering operation. So those are sort of the two of the key things. Now, back at the same time, when I was at GC Marconi, I was provided with an Italian specification. And we had this translated, and basically what it was a specification how to test boards. And I did a lot of work on this back in the 80s. And what we tried to do is test in line with the specification. The problem was at that time is that it was trying to be a specification. It was trying to measure something which really is extraordinarily difficult. So you can't measure the size of the result, the number of results you get from this sort of test, but visually you can see where there is an issue. So it was a great comparative tool, a great way of understanding what was going on rather than actually setting a criteria for it. Although I must say, a good friend of mine actually produced a piece of equipment which would give a numerical value to outgassing, which I'll mention a little bit later on. So there was something. So this specification we used, it's never been included in the international standards. It's only ever been shown as a reference source or a comparative tool. But hopefully you'll be able to use this test. And as I said, I've been using it for more years than I care to remember, testing boards for customers, because it is something I can do very, very simply for customers. So let's look at where we can use this test. First of all, if you've got plated through holes, which have got pinholes and blowholes in from a soldering process, what's actually happening is that During the soldering operation, gas is trying to get out from the plated through hole, and it's creating pinholes or blowholes, which is what we refer to. But when you're soldering, the printed circuit board is going from, let's say, ambient up to 150, then up to 200, 250 degrees Celsius during a typical soldering operation. And the solder is added to the plated through hole, and during that operation, obviously, any moisture which is present in or around the plated through hole barrel will turn to steam and want to escape from the plated through hole. And it'll either go up or down, depending on where it is in relationship to the top or bottom of the plated through hole, and whether or not there's some sort of restriction. As if you're wave soldering or selectively soldering, you will generally find that the top side of the joint will solidify faster than the bottom side as the board exits the solder wave or the solder fountain. So consequently, the top is sealed, so any energy which is still present will go down. So that's why we tend to see more evidence of gassing on the bottom side of the board rather than on the top side of the board. And again, you can do this yourself by simply taking a board which has got outgassing in it and try and do it from both sides and see if you see any reaction taking place on both sides in your experiments. So if we then take a printed circuit board with a solder joint in, as you can see in this illustration, and we apply a soldering iron to the solder will reflow again. And what we should be able to see, if we could look inside, is there would be gassing. But sometimes what you can also see is little solder balls jumping out of the solder surface. And if you do this under 20 times magnification, you can very easily capture it on video and demonstrate to people. Now, people would argue, potentially, that there's some other contaminant in the hole. The contamination is coming from the solder, the flux, and everything else. But 9 times out of 10, it's always the printed circuit board. But please don't always say Bob Willis said. It's always 100% it's that. It's not always. And I'll show you a few examples why it isn't later on. But if you do this, this is a simple way. Just touch it with a soldering iron and watch. Don't add flux, don't add solder to the soldering iron tip. Just add the heat to the joint and allow the solder to reflow again. And you'll see evidence of outgassing. But again, you get the arguments that something else is causing this. So that's why I want to demystify it and make it even clearer and simpler for you. So that's dealing with a board which is, has been soldered, or dealing with a board that you want to examine. But if you're going to take the variables away, what I suggest you do is take a printed circuit board and basically desolder it. So use a standard desolder tool. I'm sure you're all familiar with good quality vacuum desoldering tools, which is really the only tool you should be using in our industry now, not these horrible solder suckers that cost $2 each, which are more likely to damage the board than actually desolder it. So a proper vacuum desoldering tool, and we remove all of the solder from the plated through hole, going through proper procedures. So when you've removed the vacuum and the tool, you can remove the pin without any damage to the plated through hole. So that then allows you to test the board. So it allows you to break down the problem. You know, what's causing the issue? Is it something other than the printed circuit board, by removing the variable, which is in this particular case the component or connector? So if you want to test the board, a bare board or an assembled board that you've desoldered, what you do is you take the board, as I illustrate here, and you put some oil into the barrel, as I show you here. And what you're trying to do is just put a very small amount of oil. We're not talking about a lot of oil, just enough to fill the plated through hole. What I like to try and do when I do this is just also take a little piece of blotting paper. This is just to take out a little bit of the oil, just a fraction of it, if you've got any bubbles in the oil. Because if you put oil in, sometimes there might be one or two bubbles there. And if you're going to record this as a video, as I do for customers, or I'm going to take some photographs, I don't want there to be voids to start off with, because then somebody could argue that they were still present before the test. I think it was a very bad argument. You're not going to win, but I'd rather try and eliminate the issue. So put a little bit more oil in, or just use a little blotting paper. Now the oil, what I refer to it as colour the balsam oil. Colour the balsam oil. Now this oil is readily available from any microscope supplier. And it is the oil that we used to use before we started to use non-contact lenses. So there was a thing we used to use called an immersion lens. And it was a high magnification lens, about 100 times magnification. And we would put oil between it and a microsection. And the idea was it collimated the light and enabled better quality of imaging, magnification, etc., etc. Today, most people go for the more expensive lenses, which are, non-contact or non-liquid lenses. But this is what the oil is used for. So it's called colour the balsam oil, or it's called microscope immersion fluid oil. And again, all you need to do is speak to Olympus, Carl Zeiss, Nikon, any of the suppliers of optical inspection equipment, and they'll be able to supply you a bottle. And it costs around $30 for a little bottle. It will last you months and months and months. So it's not exactly going to cost you a fortune, this particular test. So we've got oil in the hole. We can see through the plated through hole. And the idea of taking a little bit of oil off the top, as I illustrate, is it's showing you, it's giving you a different view, because as you know from photography, if you've got this this shape, you're getting a better view again of the edge of the plated through hole, as we'll see in a few moments' time. Next step is you get a number 6 iron. I'm still working with the traditional terminology, number 6, which is used to be a Weller tip, in number 6, 600 degrees Fahrenheit, but it could be 6 or 700, number 6 or number 7. But really, we don't want to use too high a temperature. It's just enough to cause the water vapor, or the water or the moisture in the board to turn to steam, to allow us to see it visibly. So you can go for your lowest soldering iron temperature, but I normally use 600 Fahrenheit, and that works fine. And we're just placing that on the pad adjacent to the plated through hole, or we're placing it on the track, again adjacent to the plated through hole. Now, the reason I do it in this way, rather than immersing the whole board into oil, is it's easier to clean up afterwards. Because if you had to use the board, you could clean locally, remove this, and it would not stop you soldering. You may have to go through another cleaning operation if you were going to do something else to the board, but honestly, you could do this and still use the printed circuit board in a lot of industries. There are probably some that you can't, but there's probably not necessarily a reason why. But again, I'll leave that for you to discuss with your quality guys. But simply, you should be able to have a sample board you can test. We then wait and see what happens. And what should happen, if you've got any thin plating, breaks in the plating, or you've got voids in the plating, you will see bubbles. So you'll be able to visibly see this. And this is what I do when I show people, when I'm testing their boards for them. You can see the bubbles visible coming out, and you can see specifically where they come out. So if we look at this photograph to the right-hand bottom of your screen, you can see some bubbles. So this is just a black and white image, but you can see it. Very, very obviously there are bubbles present. So that makes it nice and clear. Now, I mentioned that one company or one person made a machine which could quantify this. And you might find this a little strange, but it was called a plopometer. Basically, it counted the number of plop, 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 plop. As the gas escaped from the oil, you got a little plop. And this gentleman has retired now, is living on a very nice island in the Mediterranean, and he certainly doesn't make these, but it's just a nice story. But he never commercially made it available. A plopometer, a gentleman called Dr. Brian Ellis. So now a couple of examples. Now, I've got two examples here of boards, and the first one shows what I call subtle outgassing. So you can see outgassing visible as the gas comes out and breaks on the surface through the oil at 1 o'clock and 9 o'clock. But you can see that's quite reserved. It's not, tremendous amount of gassing, but certainly that did and would create voids within the solder joint. The other thing is, you notice that went on for a little over 15 seconds. So if we think about hand soldering and desoldering and also selective soldering, that's going to go on for a lot longer than that. So that's why when you come sometimes to rework a board, you still get that gassing still present. Now on the right-hand side, another video clip where you can see much more vigorous, much more volume of gassing from this particular plated through hole. So again, exactly the same test being conducted, looking vertically, and you can see the degree of gassing from the printed circuit board. And again, if you start to study these in more detail, sometimes you can see, and doing some inspection beforehand of the plated through hole optically, not with a microsection, but optically, you can sometimes see the position in the plated through hole where the gassing is occurring and whether it's related to something else in the PCB manufacturing process. Now, the gassing this test can be used for pads which have got vias in. These are just two examples of boards that I was testing for a customer. And what you're looking at is where the test was conducted, just over the via. Now, it is generally unusual to see gassing from vias, but it does happen. And certainly, sometimes it can happen more than we might see on some VGA components if you're mounting them over vias, which you shouldn't do, but in the real world, sometimes people do. So you can do it on via holes as well. And these are two blind via holes that we're testing in this example. Now, in addition, we have printed circuit boards which have vias in, as we all know, and sometimes people will actually fill those vias with epoxy resin. Now, if you're mounting components and reflow soldering them on the printed circuit board, and you're mounting them over vias, as in this case, this is a good example of outgassing from the board and from the vias. Now, in this particular case, this led to voids within the solder joint. In this particular case, I'm not putting oil into the holes, I'm putting oil over that center pad underneath an LGA QFN, and I'm heating up the whole of the board to simulate the soldering conditions. And again, you can see quite nicely how outgassing has occurred. Now, in this particular case, it could have been the epoxy, which is filling the plated through holes, or equally, it could have been the quality of the plating in the holes. I was not asked to differentiate between the two for this particular customer. I was just able to demonstrate that it was the board which is issue, not the solder paste, not the profile or the stencil pattern design that was being used in this particular product. So, I've shown you a test method of outgassing, and I've illustrated some variations of what we can do. And these are a couple of other examples that we do get from time to time, which is bubbles in joints. And these are no plated through hole, these are just vias with solder in them. And one of the problems, if you do have vias with solder in that you filled on side one of a board, so if you've done first reflow operation and you had solder in the via because it was a solder level board, etc., and you've got outgassing, then it's perfectly reasonable to assume that you could get this effect. Now the problem here is that if you then want to print side two of the printed circuit board and you've got lots of bubbles on the joints, or you've got these slightly deformed joints, then it's going to really give you a problem during the screen printing operation. So again, you just got to think about those examples as well. This example video on the right hand side just shows me testing a plated through hole with solder in, and you can quite simply see how the solder is ejected. So if you've got a problem where you're seeing solder balls which are present on the top side of a printed circuit board, or even around joints that are or have previously been soldered, and then you're just reflowing the board again, perhaps if you're doing lead-free and then low temperature lead-free soldering as a combination process, again that volatility can cause solder balls. And being able to prove that it's that and not the quality of the paste or some other part of the process is very, very important, and it's a simple thing to do. Now, moving off subject, if you like, slightly, and just to demonstrate how we can get outgassing from other things other than plated through holes. As I said, 99% of the time it's related to the board, but sometimes we can get voids in solder joints, which again, not paste and not profile related. They can be the components. So in this particular example, I'm just showing you a capacitor, multi-layer chip capacitor, which is being reflow soldered. Now watch the termination of the component, not the solder. And if you look very carefully, you can see the surface of the plating, which is actually gassing. You can see very small bubbles forming on the plating. And what this is some form of organic residue, contaminant in the plating, which is actually outgassing from the surface of the termination during the soldering operation. So that's fine, it's not really going to cause you a problem, but what it will do is generate voids within the solder joint. Now, again, that may have no impact whatsoever, but it's creating voids, and if everything on your board looks perfect and you've got some voids in some chip components, test the chip components, because that's probably likely to be the cause. So in this couple of examples I show you here, this is an optical example and a microsection which shows voids, and these were all caused by outgassing from the plating on the termination. Nothing to do with the soldering process, it's a component issue. So you can differentiate between the two with something like this. This is another ad hoc test that I've done for customers just to demonstrate that it's, in this particular case, the component. Now, as we moved to lead-free technology, the majority of the industry went away from tin lead on terminations of components to tin. And we did see, in some instances, problems of voiding, micro-voiding, but also outgassing from plating. And this is just a very bad example, first off, a very bad example of that. You can see if you look at this pin on this component, how you've got a very, very rough surface. Now, all we've done here is brought the pin up to soldering temperature, and you can see the reaction on the surface. Very poor indeed. We may well have been able to make a good reliable joint, but there certainly would have been a lot of voiding present in the bulk of the solder. In this second example, what you're looking at again is a pin, and what I've done here is again reflowed the pin. I've added heat, and if you look carefully at the surface of the pin, you can actually see it gas. It's like gassing or slight de-wetting that you're seeing visible on this particular example. So This created lots of small voids, and I'm talking about hundreds of thousands of small voids as opposed to a few. This actually did have an impact on the strength of the solder joint because of the gassing from the pin. And I've seen it a number of times with different customer evaluations, this particular problem. So back to our conversation, which is outgassing from printed circuit boards. These are just two examples of holes in joints. And you may or may not believe this, but one of the jobs I had as a young engineer in 1990 was to actually create standards for blowholes. And so how do you do that? Well, basically what I did is I took some stainless steel wire, I added it to the joint area, and then I soldered the plated through hole. I then pulled out the stainless steel wire, and there was a void. So I actually created holes of a specified size. Now, I would not recommend you do this, but I was required by my bosses to do this. So people had a reference what was acceptable and what was not. And by using the stainless steel wire, you were able to gauge the size of the void. And I wish I still had some photographs of those ones that I made in the 90s, but unfortunately I don't. So gassing, as I've mentioned, is related to the quality and thickness of the copper plating. So in this example, you can see on the microsection on the right-hand side where there is no copper present. So the bubble is around where there's no copper on the plated through hole. And these were examples of some of the worst boards that I have personally been involved with making as well as assembling. And when I was examining the boards with microsection, it was like a string vest. The quality of the copper plating was really, really poor, and it was surprising we were able to automatically solder all these boards ourselves, but we did. Now, these boards were part of a study, and basically we took boards that were destined to go to Australian Telecom, as when we were working for British Telecom, and we made a batch of boards. They were very, very poor, but they had voids and pinholes in the joints. But we decided that we were going to do some testing. So we did environmental testing, shock, bump, random vibration, temperature cycling, industrial gas testing. And out of the whole of that exercise, we had one component failure, not a joint failure, one component failure. Now, I'm not suggesting that you can accept anything, because one of the problems where you've got variability in a solder joint, it looks different. It makes it difficult for inspection departments, and it also makes it more difficult for automatic optical inspection. So what we're trying to achieve is consistency. So by specifying boards correctly, eliminating the variables, which is the quality of plating, and getting the correct plating on a plated through hole in line with standards, then you eliminate the potential for rejects being produced. Now, I included here a cross-section, and this is a board as being produced, if you like. It's being fabricated, and what you see on the left-hand side is a normal hole that's been drilled, and you can see this sort of patterning where it's copper or gold in color. And what you're looking at is the glass strands in the fiberglass, either coming across the board or coming towards you. So it's the glass strands that are pointing towards you or coming across them. And if you look on the right-hand side, there's a close-up here where you can see a darkish area, darkish green area. And that's where there is a void present. So if there is any voids present, then inevitably you're going to get outgassing. If the copper is thin, again, you're going to get outgassing. So there's where the issue is being generated from. This test is sometimes referred to as a backlight test, and it used to be done in PCB fabrication to look at copper electrolysis coverage. If you shone a light through the board from the back of the sections you see here, you see the light visible through any breaks in the copper. And then if you then subsequently plated the board with electroplated copper, there should be no evidence whatsoever of light shining through. In fact, if it's electroless copper, you shouldn't see the light shining through either. But in the right-hand side example on this page, you can see it. So the more voids that are present, the more gassing can be generated. And even on the right-hand side, as you see on this photograph, where you've got a void because of poor drilling operation, and it's fairly sealed by the copper, you can still get gassing from this surface. So if you do the oil test and then you do microsections afterwards, you may well be able to see it. Now, one of the other advantages with today's technology, and I don't show it in this presentation, but I have used high resolution X-ray. And with high resolution X-ray, you can certainly see consistency of drilling and plating, and you can certainly see if there's significant variation between hole sizes, etc. But again, it depends on the resolution of your X-ray system. It's certainly something you can see. And if there is significant voids within a plated through hole, it is possible to see missing copper, again, using high resolution X-ray. It's certainly something that we have done in the past. So back to the gassing from bubbles. Same thing is causing it: outgassing, moisture, superheating, and spurting out the solder onto the surface of the printed circuit board. You get these balloons form, but they may or may break. Now, when you've listened to me telling everybody else that it's always the printed circuit board, here's a classic example. Again, another evaluation of mine. Again, back in the 90s, I was working in a company and had to evaluate boards. And we had a problem, again, of outgassing, but it didn't make sense to me that we had this particular problem. So consequently, what I did was look at the board before and after soldering using microsectioning. And what I was able to determine that it was actually the assembly process. So this is fairly unusual today, I would suggest. But what we were doing is over-inserting dual inline components into the PCB. And you can see on the right-hand side the rupturing of the copper. So, and we certainly saw a difference between dual inline components that have a spade end termination and one that have what I refer to as arrow termination, which you can see illustrated here. So it comes down to the control of the automatic insertion machine and the setup of that machine. If it's set up correctly, there should be no damage to the plated through hole around the surface when it's added. But in this particular case, you could see it. And all of the voiding was present around the dual inline dip components, nothing on any other area of the printed circuit board, which obviously added to my suspicion that we were looking for another cause of problems. Now, blowback. Blowback is something that, again, you can see during a soldering operation if the top side of the plated through hole is covered. So I show you two examples here. One, you've got a turned pin turret terminal on the left-hand side, indicated by the yellow arrow. And on the right-hand side, you can see a clenched capacitor lead, which has been clenched and indented to give you a fixed standoff height. Some of you may be aware that when you have some capacitors where they're covered with epoxy, the epoxy can run down the lead. So then when you put it into the plated through hole, the epoxy sits within the joint. In my personal opinion, I don't think it has ever caused a problem at all. Again, it's my personal opinion. But this denching, this deformation, if you like, of the lead allowed the epoxy to stop, never get into the joint, but it did in fact seal the joint, the metal sealed the joint, and consequently you could get blowback from the flux when it was trying to evaporate from the plated through hole. The whole point about leaving a plated through hole open on the top side of the board is to allow volatile material to escape. And part of that is the flux. When it volatiles, during preheating and during soldering. So consequently, if you stop material going up, it's going to go back down. So that might be the reason why you're seeing blowholes and pinholes on joints and not outgassing from the board. So please evaluate different aspects. Don't always blame the board, although it is most often the board. Please look at other areas as well and try and prove whether it is or it isn't the PCB. Now, these are what we refer to as sunken joints. It's a term that I've used, and you get the same type of phenomena again when you've got outgassing, particularly where you've got holes which are not filled, there's nothing else in them. And as you can see on the top of this image, you've got dual inline component leads, and they're pushed up hard against the wall. So basically it's a big hole with solder in. So when the solder's in a liquid state, when it's going through the soldering process, the solder can fall out depending on the hole size, and it can do in certain situations and certain temperatures, but it's more likely again to be gassing. But because it's not a small hole, everybody thinks it's something different. If you test these, I pretty much guarantee you'll see the same phenomena as I've shown with the oil test that you've seen previously. So, is this a pinhole or blowhole? No, it isn't. It's neither. It's poor wetting. Again, some people refer to this as insufficient solder. Well, yes, it is. It's perhaps not enough. But the issue here is a burr, and it's not a plated through hole. It's a single-sided board. So with single-sided boards, when you've got open or partly open joints, it is very rarely to be outgassing because the plated through hole is not there. You've got bare laminate material, or bare paper-based laminate material, but all the gas that might escape would go up rather than down. And it's more likely to be a burr on the edge of the pad, or the hole to lead ratio during soldering is incorrect. So it's a design phenomena rather than anything else. But look closely and you can see how the solder is trying to wet to the edge of the hole or the edge of the pad which is left behind, but it's finding it difficult to do so. If you look at these two examples, again, would be referred to sometimes as voids, contamination, outgassing, but this is solder joints which have actually been contaminated. So very often seen on chokes and coils where the encapsulant used on the coil or choke has run down the legs, and when you insert it into the plated through hole, you find it difficult to solder because that encapsulant material is still present there. Again, some people say it's poor solderability. It's not. It's something which physically stopped you soldering a pin, but it's contamination on the pin. If you were to test this pin individually, you'd probably find it wetted beautifully. So again, that would confuse you possibly, but make your customer happy. Now, contamination on a printed circuit board is something we all have from time to time, but in this particular case, solder contamination on gold boards is something that a lot of people have problems with. Now, if the pad is not going to be used for something like mechanical contact, or it's not going to be used for wire bonding, etc., does it really matter? I would suggest it doesn't matter. But please try and eliminate the reason why you've got it in the first place. So spitting from a plated through hole or a via hole during the soldering operation will cause solder to contaminate surfaces. And this is an example of where that could occur. I find specifically in the medical industry that they are very hot on this. So any contamination like this may cause a product being produced for the medical industry to be rejected out of sight. I personally do not understand that from a reliability point of view, but I accept the fact that different industries have different standards. So again, just you can demonstrate, you can test and understand what the root cause of the problem is by using the oil test which I've previously shown you. So what I've tried to do in this webinar is talk about any issues related to outgassing from printed circuit boards which cause voids. I've demonstrated the test method, the procedure. I will send you a copy of this test procedure with the slides so you can try this out for yourself. If you don't feel you want to do that, you want boards tested, I'm more than happy to do that also. But again, hopefully, you'll be able to use this technique successfully yourself within your own company. So just a reminder that my webinars, the next webinars that are coming up on ball grid array failures, simulation of reflow, and ball grid array rework and repair, and others throughout the year. Once a month, I run these events. And of course, you can always check out the archives of all of the webinars I've done over the last 5 years. And of course, we have a webinar demand service where you say, I want a webinar on a particular date and time for your company and your team. We can do that as well. So, any questions? All you need to do is type your question directly into the control panel, and I will do my best to answer those questions for you. I've just had 4 questions in so far, so I'll start off with those first of all. And please just type the questions directly into the control panel, and I'll do my best to answer them for you. So first question, might outgassing cause solder splashes, extrusions under QFN packages, the center thermal pad, or similar components, particularly at second reflow step? Good question. I have examined this type of phenomena before for other customers, and I have found that to be the case. But the solder has to go into a liquid state. So if you're looking at a QFN on side 2, you may or may not get that part to go into reflow underneath that center area. It depends on how thermally insulated that part is from other parts on the printed circuit board. Inevitably, when you heat up a board to 240, 250 degrees C, every solder joint on that board can become liquid, but some do not become fully into a liquid state. If you're looking at QFNs where you've got badly positioned or badly designed vias, and there is significant gassing from the vias on side 2 reflow, and you see the solder joints on the QFNs reflow again on the bottom side, then yes, that could cause that particular issue to occur. I've seen this demonstrated myself for a customer using the X-ray technique that I've shown you previously with the plated through holes. I've done it with underfill. If you've got underfill and you've got gassing and you've got solder present, the solder can actually extrude through the underfill and actually come out through the underfill as a defect. So you can actually see balls from BGAs reflow underneath the package, and then literally that volume of solder can extrude to the outside. And I've also seen that during rework and repair, where we get exactly the same phenomena with adjacent components. So you're reworking one component and the adjacent component reflows, but it's held in place with the underfill material, but the solder expands during the heating process and literally extrudes out. So I have seen that type of phenomena. Right, so what is the recommended baking temperature before underfill, temperature and time? You've got to look at how much moisture the board's expanding has in present. You've also got to look at the solderability of the finish you're going to be using if you're going to do second stage assembly. So there's a number of different factors. There's no, it's this, it's that. Even if you go to the IPC standards, they recommend, this amount of time, this amount of temperature. But really, with the greatest respect, that's rubbish, because you need to understand the design. Because if we're talking about a small mobile phone, or we're looking at a very large, complicated computer board, the time and temperature is going to be different. So I'm not trying to dodge the issue. I'm just saying you've got to do your own homework with some form of measurement. And although I don't like weight gain and weight loss because it's very boring and difficult to do and time consuming, that is a way of doing it. Another technique that some of my colleagues used at MPL, they did capacitor measurement. So basically, they took a test board and did measurements of capacitor change based on moisture and baking out a printed circuit board, and were able to determine what one board might require as opposed to another. But where you've got hundreds of thousands of plated through holes, that may bake out quicker than the same size of board and thickness of board with just 100 holes in. The reason being there's more area for moisture to escape. Moisture escapes from the edges of the board, not from the center of the board. It escapes through holes in boards that are non-plated. So they are the more porous surface, so it allows them to escape, but also moisture is absorbed more readily from those areas as well. Next question is, can you get away with thinner plating and just accept a plated through hole will outgas? I assume yes, because I've never seen or been able to demonstrate that pinholes and blowholes of the examples that I've shown you have an effect on quality and reliability. I have shown that where we've got outgassing from pins, etc., produced hundreds of thousands of very small voids, and they are mechanically much weaker than just one void within the solder joint. So again, it comes on to what you're looking and what you're analysing. Okay, next question. Have you had any issues with other contaminants in plated through holes? Yes, I've had problems with solder mask being in plated through holes, but I've never demonstrated or been able to show that that in a small, thin liquid form has ever outgassed to the extent that I've demonstrated in some of the tests. So I've seen that. I have experienced blowholes and pinholes during wave soldering with oil. Back in the day, back in the sort of 80s and 90s, it was not uncommon for Hollis Engineering or users of Hollis Engineering equipment to use oil within the solder wave. It was pumped into the solder or it was floated on the surface of the solder. You had to clean the boards afterwards, but that was just what you had to do. And one of the nice things about having oil intermix or oil on the surface of the wave was you get much less dross generation. You got a smelly wave solder machine, but that's just a consequence of the soldering process. But if you pump too much oil into the wave, you can actually create voids with oil in. So when you actually reflow the solder joint again, or pop the solder joint with the soldering iron, the oil spurted out. It was quite spectacular if you were videoing it, but we don't have that today, so that should never be an issue to you. So I honestly would say to any PCB manufacturer or any customer that if you've got an issue, it's more likely to be the boards, but all I'm saying is please look at other issues that might cause the problem, and just look at the test. That test with a simple oil, watch what's going on, is just such a powerful thing for such a simple thing which costs you virtually nothing. And as I said, you should be able to do the test quite nicely yourself. Right, so that's the 5 questions I've had so far. If there are any more questions, please type them into the control panel. I'll do my best to answer them for you. A reminder though, we'll be sending out a copy of the slides plus a procedure on how to do testing yourself directly after the survey has been completed when you exit the webinar this afternoon. So I'm just going to stay quiet just for 30 seconds or a minute, which you may appreciate. Just give you one final opportunity to type any more questions that you may have. Okay, well, that looks like no more questions, so hopefully it's been all nice and clear. So once again, thank you very much for participating in this webinar this afternoon. This is just one of the sort of simple tests that I use for evaluating issues in manufacture. Hopefully you found it useful. Hopefully when you do it yourself, you'll think this is great. If I ever have a problem, hopefully you will not ever have a problem with boards, with outgassing, etc. in. But again, it's a simple tool to be able to prove a point visually. And I've always said, if you can show a problem happening under video, optically, or whatever, you're closer to solving that particular problem. So once again, thank you very much, and good afternoon to you. Good afternoon.